Hi, so in today's video we are going to look at another example of related rates. A baseball diamond is a square 90 feet on a side. A player runs from the first base to the second base at a rate of 16 feet per second. At what rate is the player's distance from the third base changing when the player is 30 feet from the first base? So like always, I suggest that you read the problems three times and make sure that you identify the important information given in the problem. So for example, in this problem, we are being given that 90 feet is the length of the side of the square of the diamond. I don't know if that's a standard length of a baseball diamond, probably it is. Also, there's a player that is running from the first base to the second base, and he is running at a rate of 16 feet per second. So from our previous discussion, we know that every time there's a unit of feet per second or meters per hour, they are derivatives. So 16 feet per second is a derivative. The problem is asking for the rate of the player's distance, so pay attention to that. Our ultimate goal is to find the rate of the player's distance, and the distance is measured from the third base to the player. We are also given that a player is 30 feet from the first base. So we are going to illustrate first a baseball diamond. It is a form of a square. So here's the home base, and the first base is to the right side. So the second base and the third base is to the left side. So there is a player running from the first base to the second base. I'm going to represent that with a blue circle. And this player has a distance from the third base. So I'm going to construct a line from the third base to the player. I will use a dashed line to signify that it is just an imaginary line that represents a distance between the third base and the player. After some time, the player is closer now to the second base, and as you can see, the distance between the player and the third base is a little shorter than before. As the player gets closer to the third base, the distance between the player and the third base is also getting shorter. We are going now to put the important information in our illustration. For example, we know that the length of the side of the diamond is 90 feet, so let's go ahead and put 90 feet. This 90 feet remains the same as the player runs from the first base to the second base. It's important that only those quantities that remains the same you are going to include in your illustration. Those quantities that changes as time goes by, you have to represent them with variables. For example, the distance between the player and the first base is not fixed, it's in fact increasing, as well as the distance between the player and the second base, and also the distance between the player and the third base. So I'm going to use the variable x as the distance between the first base and the player. I will also use y as a distance between the player and the second base. The distance between the player and the third base, I will represent that with letter z. Now, as soon as we have this illustration, we are going to identify the important information from the problem. Let's go back to the problem and identify specific values mentioned in the problem. For example, we have the rate of 16 feet per second. So this is a rate, and as you can see, this is the rate of the player's distance measured from the first base. And so therefore, 16 feet per second is a derivative of the x, because x represents the distance between the player and the first base. So we can say that the dx dt is equal to 16, and it's positive 16 because x is getting longer, or it is increasing. So dx dt has a value of 16. Also, we have the number 30 feet, and this is a specific distance between the player and the first base. So x is equal to 30. And the question is asking for the rate of the player's distance from the third base. And the player's distance from the third base is represented by z, and so the rate of that distance is represented by dz dt. So our final goal is to find the value for dz dt. Now, once we have identified the given as well as the main question of the problem, we are going to find now a formula that will allow us to find the dz dt. So let's have a very quick look at our illustration, and hopefully we can identify some formulas that relates all these variables and constant together. For example, I hope you can see that there's a triangle that is formed between the third base and the second base. as well as the player's position. So also this triangle is a right triangle, and because of that we can use the Pythagorean theorem. I'm talking about the values 90, the y, and the z. So together they form a right triangle, and therefore they satisfy the Pythagorean theorem. Because of that, we can say that y squared plus 90 squared is equal to z squared. Now, once we have this, keep in mind we are going to look for dz dt, so we can just get the derivative of the left side of this equation as well as the right side. The derivative for 90 squared, because it's a constant, is 0, and the derivative, of course, for y squared is 2y dy dt. And the derivative for z squared is 2z dz dt. Now let us identify the important quantities involved in this equation. We know that we are looking for dz dt. Since we are looking for the value of dz dt, we must have the value of y. Unfortunately, we don't have that. The only given in the problem is dx dt as well as the value for x. We also don't have the value for dy dt, and we also don't have the value for z. However, as you can see in our illustration, x and y together form one side of the square, and the length of the side of the square is 90, and so therefore we can say that x plus y is equal to 90. We can make use of this, and we can also make use of the fact that x has a value of 30. So if we substitute x with 30, we will be able to find the value of y. So y has a value of 60. Also, we can find the value for dy dt by using the same equation. We are going to get the derivative of the left side, the x plus y, and we will get also the derivative of 90, which is obviously 0. So we get the derivative of x, that's dx dt, and y is dy dt. Now we are going to substitute the value of the dx dt, which is 16, and to solve for dy dt, we say dy dt is equal to negative 16. We are only looking now for the value of z. So to do that, we are going to make use of the Pythagorean theorem. Because z, y, and 90 form the side of a right triangle, we can say that 90 squared plus y squared equal to z squared. We have now the value for y, which is 60. So we substitute that value into this equation. So we have 90 squared plus 60 squared equal to z squared. Adding 90 squared plus 60 squared, I have 11,700. And if we are going to square root that, the simplified form is 30 times the square root of 13. So this is the value for z. So now we are going to substitute those values. So we can say 2 times times 60, which is the value of y, and the value for dy dt is negative 16, and the value for z is 30 square root of 13. If we multiply 2 times 60 times negative 16, we get negative 1920. And the right side is 2 times 30 is 60 square root of 13. We are now going to divide the left side and the right side of this equation by 60 square root of 13. And we are going to simplify that, and we get negative 32 over the square root of 13. If you are going to type this in your calculator, this is approximately negative 8.87. And so this is the rate of the distance between the third base and the player. As you can see, it's negative because that distance is getting smaller or decreasing. The unit for this distance is feet per second. This is the answer to the problem.